welcome everyone. This is Maciek Malawski here today. Marian is on his short vacation, so that's why he asked me to run the seminar today. And at the beginning, we have a short kind request to you to look at this survey about computational medicine, which is a part of our Sano project. So we would like to ask you to go to this link, which is on the screen, and you can see it also on the chat window, where there are a few questions about computational medicine, technologies, and potential benefits. So this is very important for our Sano Center to better understand what are the possibilities, what the users may need from the technological, from the research, from clinical, from business perspective. So please take a few minutes to fill this survey. And I think we are going to go to our presentation. Our guest today is Dr. Alessandro Crimi from Sano. He's now the leader of the research group on computer vision with specific focus on neuroimaging. So he will explain about his research, but we can also note that he is originally from Italy. He got his PhD from University of Copenhagen, also MBA in International Health Management at University of Basel. He worked in Italy, France, Switzerland as a researcher, also in Africa, working on different topics regarding mainly neuroimaging, various diseases. So he's now leading his lab at Sano, and today we are going to hear about the new and future trends in neuroimaging, gradients, oscillators, attractors, fractals, and more. So yes, with that, Alessandro, I invite you to share your screen with the slides, and all the floor and the screen will be yours.
Not necessarily my research, but actually things I always like to investigate and look around, or at least talk about it. I will be happy to use this opportunity to discuss with you about new things. And actually what we do here in Sano or in other places generally is that we try to find some biomarkers for in imaging, or to identify better some disease, or to highlight if some treatment is working or not, or similar things. But obviously, generally, the situation is a bit more complicated. In fact, imaging is just one. We can consider neuroimaging just as one phenotype, while the human being is a lot more complicated. So we start from genes, from genetics, which is like we can say the source code of life, going to more complicated structure networks, interaction given by the proteins, then ending up in some bigger system like the brain, and ultimately, which we are interested is either in studying behavior or a disease, why diseases arise, and why we end up having some people end up having Alzheimer or not, or brain tumor or stroke or so on. So the picture is a lot complicated. So when generally what we usually do is like we look for some specific features, for example, in neuroimaging, and how they are related to a behavior or a disease, while we forget that there is the rest. And that's actually wrong, because we should take into account the entire picture. I started reading this book some time ago, which is like making a comparison between what is, how can we move from what is genetics to something more structure that is defined, for example, a neuron, or even something simpler, as we think like a plant. How do we know the genomic of a plant, of how it's branching trees, and how then these branching trees might evolve in a disease or not, or a behavior. And I found this very interesting, because this text was more like a series of discussion between a biologist and an artificial intelligence person. We're discussing how life or intelligence arise, and then ultimately disease, which is how do we can connect. And the conclusion was simply that it's complicated. And just to have an idea, was behavior, emerging behavior, also plants have their own behavior. Like there is this fact of shyness of the crowd. I don't know if you can see, like trees don't touch each other. So it's we always think that plants don't have a behavior, but they probably do. They have like this kind of shyness. So the major question is, how do we move from genomics to more complicated structure to disease? And this, I tried starting answering this question, but it obviously is very complicated, especially if we consider humans. Some people manage to do it with a worm, with a C. elegans, but of course, a worm has just 302 neurons, but a human being is complicated. And also there are other things in life that might activate some proteins, or other things that are in nature that might change. So the relationship in humans are complicated. I tried to answer this some time ago with a former student, where we try to define like a space of considering like genetic expression of some genes. How is this impacting the connectivity, and which not necessarily is just a direct interconnection, as I was telling you before. Maybe the gene is creating some proteins, and these proteins are reacting with other misfolded proteins, and in the end they are causing the death of the neurons, something like that. But we can observe just an intermediate step, which is the structure in the brain, and ultimately how the structure in the brain is related to clinical dementia. So how the fact that changing the structure, some people then start forgetting things, or maybe they don't take care of themselves, or other things related to Alzheimer, that in this case was Alzheimer. So, but of course there can also, this point of view can also be generalized to other disease. This obviously is an overly simplistic view. So things I was telling, I'm perfectly aware that they're complicated. And also the way how we try to answer this was simply correlating things, like correlating that one gene was related to a specific change in the network, and then this specific change of the network was related to a disease or a change in behavior, which obviously, as I was showing you before, it's like jumping from here to here to here. So we are ignoring the overall structure. Now, this is more like kind of how would I continue to study to investigate this relationship. But for the sake of time in these discussions, I will cut this entire part of the of interaction with genomics or proteomics or other states, intermediate states, and I would like to focus more with fancy tools that I think might be interesting to discuss related to neuroimaging. So I will still remain focused on the on this intermediate phenotype, or discussing new tools that might be helpful us to understand this, how a disease is evolving, or what is the impact, or if we can find a new biomarker, or a new way to measuring a disease. And I start from things that are not so exotic, so that hopefully they are like kind of used by a very long time. So that we usually look at neuroimaging generally in two ways. One is the structure. So we look at how certain connections are in the brain, and this can be at the micro scale with some technology from microscopy, or on macro scale with non-invasive tools like magnetic resonance imaging. And then there is the function. So function is a bit more complicated, blurry definition. So for example, we can look at the hemodynamics of blood in the brain, or other metabolic biomarker in the brain. And there's always been this dichotomy. So usually certain people were looking at how changes are in structure and how are they be seen from the point of view of function, like of either hemodynamics of blood, or maybe misfolded proteins that are detected in the brain. While obviously there is kind of some kind of correlations between relationship between the two. To simplify our life, generally what we do is that we move from this kind of spaghetti representation, which is hard to manage, although it's still used from certain contexts for brain surgery. So they still use this kind of representation given by tractography. That is coming from diffusion MRI, and we merge this to kind of some kind of anatomical knowledge given by atlas, starting from centuries ago to more modern atlas. And what we do is like we try to simplify the spaghetti into a graph. So for example, that we move from, we know that there is this region and this other region, and we count how many connections are going from one region to another one. And instead of looking anymore to these spaghetti things, we just put one line, one edge. And this is supposed to help us in making something a bit more readable or more uniform if then we are moving to some kind of more mechanical analysis, like with machine learning. This is how you will build this kind of simplification for from the point of view of structure. Obviously, I was telling you there is the other way of seeing things, which is given by function. So there is this famous picture with 3 specific areas. So I hope I can have it a bit more interactive, and where I can see the chat. Yes, I can see the chat. So I would like to ask you to look with me at this picture. So I don't want to tell you what is it. Maybe otherwise you are already sleeping after 10 minutes. So this picture is representing the hemodynamics for 3 regions of the brain. So medial prefrontal cortex, posterior cingulate cortex, and ipsilateral sulcus. And they are represented in time. So it's hemodynamics in time. So we're not looking at the structure, we're looking at the distribution for the Bolt signal in time. And we are representing, in this graph is representing like the medial prefrontal cortex signal is this orange line, and the posterior cingulate cortex is this yellow line, and the ipsilateral sulcus is in the blue line. Without me telling you what is this that is going on, can you see? Do you see something relevant there? I'm not continuing until someone is posting me in the chat. Okay, someone says PCC, so posterior singular, and someone else added anti-correlated. Yes, and you are both right. So we have that there are 2 regions that are correlating. You see the orange, let's say, dots are always kind of matching the yellow ones, while the blue lines is something correlating. And this is something that we use to reconstruct from the point of view of functional connectivity, because we say if we given a time series, for example, a signal is highly correlated, we also try to reconstruct a similar graph like the one before, where we are considering correlation and anti-correlation. What I mean with that, so that, for example, okay, you have to see the full brain, so it's not that obvious, but it's like how do I stop it? No, I cannot stop it. So what I'm saying is that, for example, if one region is correlating to another one, I will put an edge depending of the level of correlation, of anti-correlation. If there is no correlation, I don't do it. This is actually nothing. If you're working with the neuroimaging, this is nothing new. So this is just another way of seeing the functional connectivity. This is like stuff we used to do it. And there has been like thousands of works, both from the point of view of structural connectivity and this kind of functional connectivity. Because like once we have things on a graph, now either we start looking at the graph as a use the features of representing the graph, or we can even do some more complicated things like done recently, like with graph convolutional networks, or we can also apply many other things we know about complex networks. And this has been done in all possible ways. And it's actually the kind of work also that kind of people starting in my group is doing. Now, this so far is the traditional part. So what I would like to talk about today, if there can be new fancy tools or crazy tools or more modern or future trends, how do you want to call it, that can help us better understanding the brain or related disease. And then I have some answer to this question. So there are a couple of models that are like gaining attention recently, and others that are maybe more also interesting. For the sake of time, these are all for complicated topics, so I will mostly focus on the first two, and the other two I have just a couple of slides. So I start with the story of gradients, which has been like highly introduced by Daniel Marguglio, but now have been investigated by many people. And the concept of gradients starting challenging a bit the concept of parcellation. So what I was telling you before, that to construct this graph, we need to define anatomical region from some kind of features, either site architecture or a functional correlate, or rather, there must be a definition of this anatomical structure with cortical thickness somewhere from anatomy or function studies. This subdivision is coming from. Also here, so even here, if I have to consider the time signal, have to do this time correlation, I'm supposed to create this region of interest where I'm looking at the signal. Of course, unless you're looking at voxel-wise, but even voxel-wise, that should be considered a region of interest. So the idea of gradients is a bit starting challenging this concept of brain parcellation. Before we challenge it, I would like always to remind what is this brain parcellation, and there is this definition I found in popular paper from Glasser that end up also in the cover of Nature, so where they say that a cortical area is a distinct region of cortex that differs reliably from neighboring areas in one or more neurobiological properties from the four basic categories: function, architecture, connectivity, and topographic organization. So the idea of gradients, as Exotic will start seeing, actually, they have been able to show one by one all these things. So most likely, this concept of gradients should replace the concept of parcellization, although it's not that easy. So at the moment, it's just a super fancy investigation, not necessarily has been directly applied at the clinical level. And the first work from Daniel Marguglio was considering gradients from the point of view of functional connectivity. I remind you the story. This functional connectivity means that some regions in time, they correlate given their Bolt signal. And the map I'm going to show you is starting considering this functional connectivity, for example, from this region to this other region. Let's say that correlation is very high. And I was mapping back on the surface, representing that there is a peak which is highly correlating another one. If there is a little correlation to another area, it's not represented by, it's represented by another value, the value of the correlation. So what I mean here is that this is a map, not a map of the regions I showed you before. It's a map of the overall distributions of correlations across the surface. So it means that this area is functionally highly correlated to this area, but it's a little bit correlated with this area. And then here is even less correlated, and here is not correlated at all. And then here is start being correlated again, and then a bit more, a bit more, a bit more, and here there is a peak. So what was the observation is not only there is correlation between region, but there is a gradient of correlation. So that is like this very far part are like two peaks. And then as further we go from this region, there is less correlation. At some point there is like the minimum of correlation, and then it goes up, 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 up again. And it's the same from other regions. So it's like this part here, there is a high correlation with this area, then less, and then it starts again. Up, grow, 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 grow. So that this starts suggesting that maybe it's not that there are really regions that they parcellate. There is no real parcellation, but there is an overall gradient distribution of functional connectivity. And interestingly, for the kind of a signal that they modeled, there was the peaks were this region, which are known as a default mode network. The kind of data that they study was functional MRI for 1 hour resting state. Poor guy, 1 hour in the machine just for one time series. And they also validated on macaque, in the sense that they also noticed that it was not only in humans that there was this kind of behavior. I have a better picture later. And even on a smaller detail in the macaque, there was this kind of gradients of distribution of the functional connectivity. What was is that also the observations, not there was some kind of random distribution of these peaks. Was what he also noticed that they also noticed that these peaks were like the maximum equidistant point found according to geodesics. So here you see the brain is kind of inflated because I'm like they are like exploding the fact that the brain has like a gyrus and sulci. So if you consider the path at the cortical level from let's say this point to this point, you cannot draw a direct line. You should consider that there's a gyrification and then it's going up again. So this is what this inflated brain is representing, is they are like exploding this. And the reason is to have a proper geodesic distance that they can measure. And the proof was that considering the geodesic distance between these regions, actually it seems that for this specific time series signal, this point that we know already from the past that we call default mode networks, they are actually the most equidistant point. So it seems that there is an underlying organization of the brain that these peaks of these gradients are the most equidistant points. And I was telling you before also that this is has been known that it's been matched with macaque, but So there is the suggestion that there is a common phylogenetic tracks also in this kind of organization, because from previous study from Krupitzer, we know that every most of the mammals, they have the vision system, computational system is in the occipital lobe, then the sensorimotor cortex is here in the middle. So of course, this is not a proof, it's more a speculation, but there is the idea that probably this kind of organization that they found both in humans and macaque, probably it's common in all mammals. So there is probably some kind of common phylogenetic trait in the evolution where we organize better the brain in this way. It's not just functional connectivity. So other people have has also analyzed from the point of view of cortical structure in mice and also in gene expression. So they also know there is certain genes that are highly expressed in a specific point, and then they go down, 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 down. And it's the same appearing the same thing that we noticed from functional connectivity, that is appearing strongly in one point and then decreasing, suggesting that there is also a kind of gradient in gene expression. And another study also noticed that for some kind of representation of features for cortical thickness, there are also gradients. So the cortical thickness is strong in one point and is also diminishing along the surface. So what is the take-home message, at least from this part that is been, let's say, has been hot for investigated by many people, is that most likely the brain is not parcellated in a strict manner. So this analysis of region of interest is probably, it's good, it's practical. Also, everybody complains about like non-atlas, like the AL, but in the end, everybody uses it. But it's mostly likely not what's going on in the brain. So most likely it's more like this gradient organization, which has been investigated both as a functional level, also gene expression, and also cortical thickness. And what is also interesting is that there are probably some, apart the fact that this is probably some kind of, there is behind some principle of organization, it's also interesting that it's most likely common across species. So I close here, and hoping that here this was interesting for you, so I move to the other part, where if that part before was kind of strange or interesting, now we are going to move into the weird part, where I go to the other modality that has been introduced by Selena Tassoy, which is oscillators or harmonic connectomics. Before I go, I start moving back to the brain. I show you some other things not in the brain. So I show you this video, which is on music. So I don't know how much you get it from the video, but was a surface attached to a kind of speaker, and they were put in some sense, and depending which note they were playing, the sound was organizing in these patterns. So one specific note, let's say, I don't know if this was, let's say A, they were clicking A on the keyboard, and the stance was organizing like this, because there was some vibration that were going from the speaker to the surface with the sound. Or if they were clicking, pushing the B, maybe it was this. So, and this is something well known from probably 200 years, that sounds also is influenced by the surface. And other people have already modeled this kind of phenomena, like with something like Laplacian Eigenfunction, where is like Laplacian is this operator and some kind of harmonics that are representing like the frequency of the sound. And also Laplacian Eigenfunction of this kind of frequency analysis of harmonics is not has not been limited to music, but or sound or acoustic, but has been also has been noticed there are similar patterns also in other fields from quantum mechanics. And also what I kind of like interesting there, there's been some studies also that there is some specific frequency of some of how certain animals evolve their skin given the nature of their skin. I don't go too much into this fancy frequency analysis of the skin or acoustic, but just to show you that in many aspects in nature or in other phenomena, there is some kind of many phenomena are influenced by this kind of harmonic representation. So what was the insight was that not only certain things in nature are given by this kind of harmonic representation, but also the brain might have some kind of underlying summary given by Laplacian Eigenfunction. So they also investigated the extension of Laplace Eigenfunction given the structure of the Connectome. And when I say structure, I would like to stress structure of Connectome in the sense that they studied the surface and the connections within the brain. So it's more like studying the cortical surface and the fibers of the brain. It's not related to EEG or fMRI or other temporal signals. So it's not some kind of harmonics given by the time series. It's more harmonics given by the shape. And what they figure out is like doing some kind of eigendecomposition of the Laplacian, and they noticed that there were specific patterns, which was interesting because, for example, this the nine pattern was the 7th pattern was very similar to the 3 connection I showed you some slides before, like the default mode network. And what after post-hoc analysis, they also noticed that other networks that are known in the brain were kind of matching this. They were kind of matching this kind of representation as was coming from the eigendecomposition of the Laplacian on the surface, which was kind of interesting because the default mode network is something related to functional, while this is more like Laplacian on the surface. So again, like the gradients before, is probably showing that there is some kind of relationship with this some hemodynamics given by temporal signal and how the structure in the brain is organized. So the two things are kind of matching each other. Not from the point of view of gradients, but more on seen from the point of view of harmonic decomposition of the shape of the brain. So here is more, I put a screenshot from the paper from Atasoi, where they are like more representing the kind of frequency, how they, in the wavelength, how they are matched in this kind of parcellation of the brain. Again, to avoid when they were using, when they were trying to consider this Laplacian was constructed given some kind of Connectome. But to avoid the same mistake that I was telling you, to have a region of interest, a specific region of interest, this was constructed by considering each vertex for the resolution that they use of the cortical surface as a node. So they consider, I don't remember, I look in the paper, but in the end, the region of interest were like in the order of thousands, because we're given by each cortical surface. And then they given the DTI signal, they constructed the Connectome. And there is a discrete version of the Laplacian. So once you have as I was telling you before, that you can reconstruct the brain as a network, you can compute the Laplacian and do the eigen decomposition. And that's how they ended up being able to see the eigen decomposition from the point of view of the harmonics in the Connectome. Why are we doing this? That's probably if you see the online lectures to Adasoi, many people are asking, what's the point? And the idea of doing this is to have some kind of new language that can be used to represent the brain that is not necessarily limited to what we traditionally do with structural analysis and some kind of time series analysis, but more related to understanding the synchronous oscillation that we can have from the structure, from what kind of say the music that the shape of the brain can give you. Or if I want to cite someone probably more popular than me, Alessandro, so the idea is that we should look at everything in terms of energy, frequency, and vibration. Of course, all this validation were not just theoretical, they have expanded or applied this kind of formulation in a series of studies related to psychedelics. So after the seminal work from Atasoi, they substantially trying to model if this kind of representation of, and then summarize with the overall power of this harmonics or total energy of these harmonics used to distinguish, let's say, healthy control and people which have under clinical control, they have assumed psychedelics. So they look at both LSD or psilocybin, or the one I'm reporting was a control study that they had with 12 healthy participants, some of which that they have received a placebo, and half of them they have received some intravenous dose of LSD to see if there is some kind of changes. And the underlying idea is that psychedelic like LSD is kind of, they are serotonin-like molecules, so that they are creating some kind of disturbance in the brain, but at the same time, this disturbance is changing at microscopic level connections, which means it's also changing the brain, at least for this time of when the LSD is assumed, or maybe even later, we don't know. And this was their idea, is that this can be detected by these tools that they have created with the Connectome harmonics. And in fact, what they reported is that generally the subjects assuming LSD, that you can see here, they did three experiments. So just giving pure LSD, or considering LSD and music, or after hearing music. And overall, the people which were under psychedelics were showing some kind of higher power and higher energy, suggesting that this tool can be used to kind of detect some kind of changes in the brain. Of course, might be a bit speculative that they have investigated with psychedelic, but probably this can be used for with other disease or other things. But that's what was their line of studies. So I will be personally curious to see if this can be seen in a group of elderly patients and people with Alzheimer, but I'm reporting what they did. So it seems that at least can be used for kind of discriminant power between the distinguishing group of people. And summarizing, what is interesting is that this tool is introducing us some new way of seeing things, which not necessarily we can, not necessarily we have to stick to the traditional connection we see in the neurons, so structure connectivity or fiber bundles, or some kind of functional signal like hemodynamics, but maybe some kind of analysis of the surface with this kind of Laplacian Eigenfunction can be useful. Again, remembering this, Nikola Tesla said that if you want to find the secrets of the universe, you should think about energy, frequency, and vibration. Now I have the last two things that I will try to go in very quickly. So this was more related to things I've done in the past. So trying to address this dichotomy that we have something structural and some kind of functional signal evolving in time, how can we put these two things together? Also, because it's not just a whimsical way that we need to put these things together. Yes, it's also because they are probably the two sides of the same thing. So this is more a structure, and this is more what is happening along the structure, which is probably something that even people studying chemistry or proteomics, they are saying, like, there is a structure of a protein, but we are not just interested in the structure, we are interested in what this protein is doing. So also, but the two things are related. So what this protein is doing is also depending on the structure. So it will also be interesting to know, for example, going back in the brain, like that we have a specific, let's say, highway where something is moving. It can be hemodynamics, can be protein, will be interesting to know why it's starting to from one area to another area. Let's say we can think about causality, which is a bit more advanced than the graph I showed you before, because now I'm putting arrows here. So because these things are changing in time, so it means that if there is some activity here, then it's causing some other activity afterwards in another part. And this, of course, is not happening by magic, but it's happening along tracks that exist physically. So these two things have to be put together somehow. How we put together some at the same time? Historically, there's been two ways of putting things together. The most actually there were more, but these are the most popular. So one is a very complicated model that is trying to reproduce the physiology, starting from neurons to how it is changing in big region, and was introduced by Carl Friston, which is in the end is some kind of Bayesian model validating if actually one region is causing something in another one. And the other most used method was actually coming from economy, which is was more like a study, coming from like a study of evolving stock market, which is called the Granger Causality, which is more like if you see that something at like 2 time series. Actually, here was, imagine this is like the stock of Apple, and this is of I don't know, Google. So if some peak was happening in the stock of Google, then afterwards Apple was also influenced. So that these two, they were kind of a temporal relationship between the two, not direct. So there is supposed to be some kind of coefficient that you should consider here, but everything is like driven by some kind of autoregressor model, even by some coefficient. And how this thing was used in brain is that we were like trying to estimate this coefficient. So we were still considering a functional connection and which coefficient can find some kind of from the point of view of the autoregressor influencing another region. After that, we know that there was some kind of influence between the 2 time series, then we will also make some kind of sensitivity analysis. Like if then I remove a series in a simulation, then the other series is still there. So this was more like the kind of way Granger Causality was used. This is just the beginning, because obviously many people have done a lot of variation of the dynamical causal model and many other fancy advancement of the Granger Causality, but I did my own advancement. And my own advancement was given by the observation, which I was telling at the beginning, that it's not just that we observe some signal in time and then there is a coefficient. There is for sure an underlying physical structure that is relating the region. So here, for example, I'm showing you the region I told you before, like the medial prefrontal cortex and posterior cingulate gyrus, which we were seeing in the functional connectivity, and I'm showing you that there is a connection. So there is this thing, there is a physics. It's not that one region and the other region, they are simply co-activated. There must be some kind of path that is going through activating them, connecting them. So my initial intuition was that we should put together the two things. So not finding this coefficient in the traditional way that was found by with Granger Causality, but this coefficient has to be constrained by some anatomical model that we have, some underlying anatomic fiber bundles that we have. And I don't tell you the wallpaper, but my solution was that doing some kind of minimization that where I was finding this coefficient, I was kind of reinforcing that each connection were supposed to be given by the structural connection found from diffusion interesting imaging. So substantially what I was doing, I was also finding this coefficient, but forcing this coefficient to come from, to, let's say, be 0 if there was no structural connection, and so on. One thing I'm trying to expand at the moment is that is coming from more from the world of attractors, and the reason is because both Granger Causality and Dynamical causal model have been criticized that in the end they just look at temporal correlation. They are not necessarily a pure representation of causality. Pure representation of causality is probably something more complicated to prove and to show. The last thing, and I go super quickly, that's fractals. So fractals are, if you probably know this, this is the Mandelbrot set, where if you zoom here, you see this part. If you further zoom, you start seeing the same original picture. And this has been seen in other natural phenomena, like this, some vegetables or eyes, like that. If you see zoom is always the same pattern repeated to infinity. And was someone noticed that doing constructing functional connectivity, depending on which scale, so in which kernel they were considering the region, they were start seeing kind of similar way of clustering along this functional connectivity, like that these, let's say, these 4 blocks were also seen at a larger scale and also further larger scale, suggesting that there is some kind of interaction fractal-like, that we have like these repeated patterns that are seeing at lower level, that they start seeing if we increase the size of the region that we are the region we are considering for the Pearson correlation for the functional connectivity. It's maybe a bit of speculation, but it's probably good to consider also because they've noticed that some of these patterns, they were like also going to a higher level of cognitive. So like from small size of the low level of auditory processing to some speech processing to some higher cognitive tasks. So in summary, I don't know if all these things I mentioned now, they will help us to address disease analysis related to brain, like for finding the new biomarker or subgroup classification of Alzheimer's, schizophrenia, or autism, or if this can be anywhere, this can lead us anywhere. Maybe the simplest thing are enough, and the answer is probably related to something else like pharmacology or genetics, which I completely neglected today. But at least they are kind of new tools that we can take into consideration. And I remind you, they were like gradients, so not necessarily the brain is parcellated, or effective connectivity, but what is related to effective connectivity from the causality point of view. And then the fanciest other fanciest things like harmonics to represent the shape of the brain, or fractals in this kind of pattern that are repeated. So as I was telling you, I have no idea if this will be any use from the clinical point of view, but I hope you enjoy to hear this maybe exotic and new or future tools that will be used. And I am here now open for questions or discussions or suggestions or comments or whatever.
Yes,
Thank
thank
you.
you, Alex. Thank you for this inspiring talk and new ideas.